My name is Jim, and we're going to be talking about the charging and discharging of a capacitor. And one of the things we have to know about is how long it takes to do that. So what we have here is what's called a time constant, and the symbol for that is the tau, Greek symbol, and what it's equal to is the product of R times C. So as it turns out, one time constant will be where the capacitor is approximately 63% charged. And the unit for a time constant is a second. So let's begin by starting here, and it's important to note that VC initial, that's where we're starting out, in all cases, what we're going to be talking about today is 0 volts. There's another step that would be required if it were, say, to be charged to 20 volts initially, or perhaps negative 50 volts, but we're not going to be worrying about that case. So we're going to be dealing with the simpler case. And to help us understand this, let's take a look at what happens for the current at t equals 0 plus. Now the 0 plus means a tiny time increment after the switch is closed. And since the capacitor voltage would be 0, all of the source voltage would be across the resistor, and that would simply be equal to 100 volts divided by 10 ohms or 10 amperes. Now, to get the thought of a charging capacitor, let us use a battery instead of a capacitor, and I've arranged the battery here to be series opposing with a value of 30 volts, and our charging source here would be 100 volts. So as you can see by this is that there's going to be 70 volts active in the circuit, 100 minus 30 volts divided by 10 ohms resistor, so that would give us 7 amperes. Now if we take that same thought with a capacitor and we'll let him be equal to 90 volts, same thing applies. The net voltage across the resistor would be 10 volts. So under this circumstance, the current charging the capacitor when it's 90 volts would be 1 ampere. So what we're seeing here is we're starting at 10 and we're decaying to 1 ampere as the capacitor charges. Now if we were to graph this, and I've not marked off the time here in time constants, and remember that these are seconds, and in this case I don't guess we didn't specify any values here, but we will on the following page. What we see is that the capacitor voltage starts at 0 and then begins to charge toward the final voltage, which is 100 volts, and at 5 time constants later it's almost equal to 100 volts. It's an asymptote, so it doesn't actually ever get there, and the industry says that after 5 time constants the capacitor is charged. Also what we see is the current decaying asymptotically towards 0, and the thought of that is as the voltage approaches 10, the net difference voltage across the resistor is approaching 0. So the current starts out at its maximum here, which would be 10 amperes, and then decays asymptotically toward 0 volts. So both the voltage and the current have asymptotic behaviors. So to better understand this asymptote thing, let us take a look at the hull of a ship. And we're in 33 feet of water here, and it's sitting on the bottom. And 33 feet of water provides 1 atmosphere of pressure in addition to that of the air at the surface, which is approximately 14.7 pounds per square inch. So I've set this for 33 feet, meaning at the very bottom here there would be 2 atmospheres of pressure. The ship's hull is setting on the bottom. This is the static level of the water, and what I'm going to do is punch a hole in the bottom of the boat right here. Now, the larger the hole, the more water flows in, the quicker it fills up. So a large hole would correspond to a small time constant. So we're starting out here with 33 feet of pressure would be approximately 14.7 pounds relative to the surface. And as the water begins to flow in here, what will happen is that the hull will start to fill up. So at this point, the difference in pressure would be that of the surface versus that of the hull, which means that the pressure basically is decreased. So as it fills up, it'll begin to decrease, and what that means is that the flow rate into this is going to slow down. Now if we come back a little bit later, say, and the water level is here, the pressure difference will be the surface of the water to the water inside the hull, and the pressure difference is greatly reduced, so the flow of water through the hole is again reduced. So what we're seeing here is that the water rise in the hull relative to the bottom is 33 feet, is asymptotically approaching the 33-foot distance between the bottom and the hull. So let's take a step forward in time, say 10 years, and we'll say that nothing else has changed here. Water level's constant, there's no wind and so forth. And if we look at a water molecule here at the hull, it may have moved 1/10,000th of an inch, but it's still flowing in. And that's our asymptote. Also, one here, concrete hardening has a shape like this too. Only this is going to be the theoretical hardness, which is determined by the chemical mix of the cement and so forth. So what this means is when you get up tomorrow morning, your sidewalks and driveway and so forth are going to be a little bit harder than it was the day before. So that's why they keep cars off the driveways initially for like 6 or 7 days, is so they can get up in hardness here where it won't crack if a vehicle drives onto it. So charging, once again, we say that after 5 time constants, the voltage across the capacitor in this case would be approximately equal to 100 volts. And now let's talk about discharging a capacitor. So in the previous video, I charged one up and took a lead and put it across the capacitor, and the lead flashed and I discharged it through the light emitting diode. So if the capacitor doesn't have a lot of leakage after it's charged, it's going to sit there and retain that voltage. So note that I is defined in this direction, and then to discharge the resistor, all I do is close the switch, and that would be at time t0 plus again. Now, it's important to note that I is defined in this direction, and that was the direction of the charging current. So if I don't change that, I'm going to end up with a negative on the discharging current, because the actual physical current is going to be flowing in this direction. So let's take a look at this. We flip the switch, and here's our 1 tau, and what we see is the capacitor voltage starts out being 100 and then decays, approaching 0 volts, and a 1 time constant would be approximately 37 volts on the capacitor. Now the current, when it starts out here, is, since we have 10 volts across the resistor, it's going to be a maximum of 10 amperes. But since it's flowing physically in the opposite direction to the defined current direction, it's going to be negative, and then it decays exponentially, again 63% from the initial value of 10 amperes down to our 1 time constant value. And that would occur for time constant 2, 3, 4, and then at 5 we would say that the current is 0 by industry standards, and the capacitor voltage is 0 again by industry standards. So yeah, mix a little math in here, and what we know is that the time constant equals RC, and for a charging capacitor, and under circumstances, this can also be used for currents, and that's explored in AC circuits a little bit more. But the defining equation, one which would be very good to learn, is V times the quantity 1 minus E, natural number E, to the negative T, that's the physical time, divided by the fixed time of the components, which would be tau. And here I've indicated the same thing, except in the numerator of the exponent I have RC. The negative means that it's decaying relative to growing, so it's getting closer and closer to X. If I didn't have the negative there, it would look like this, grow to very high values. So if we let R equal 12K and C equal 100 nanofarads and V equals 20 volts, let's find out what, say, the capacitor voltage would be at some given point in time. So first we have to find the time constant, R times C. 12K would be 12e to the third, or EE to the third, depending upon your calculator, times 100 e to the negative ninth, because this is nanofarad, and the time constant of that would be 120 nanoseconds. So that would be one time constant here. And then I marked off in time constant values, instead of just tau values of 1, 2, 3, and so forth, the actual time. So with 5 time constants, it would be 600 microseconds. So what we want to do in this example is find the capacitor voltage at 150 microseconds. So we set up our equation. VC is going to be equal to our charging voltage, which is 20 volts. And then populate the exponent here, 150 microseconds divided by the time constant, which is 120 microseconds. And you do not need to enter in e to the negative 6 in your calculators. As long as these units are the same, you can just use 150 over 120 or 15 over 12. So that makes the math a little bit easier. And then I've done this step by step. So e to this value will give us a value of 0.2865. And then if we just subtract that from 1, multiply by 20, that shows we have a voltage of 14.27 volts. And then the question is that a reasonable value? So if we think about it, at one time constant, it's going to be here. 63% of 20 volts would be 12.6 volts about. And 150 with a value of 14.27 volts makes sense. So if you get a value which, if you just look at the graph and ask yourself the question, is this a reasonable answer, is a very powerful way of troubleshooting. Now discharge, or finding I in some cases, is simply going to be equal to, and that'll be the current flowing here, the difference in voltage across the resistor. So on one side we're going to have the supply voltage V, and on the other side we're going to have the voltage across the capacitor C. So all we have to do to find a current at 150 microseconds is to subtract the source voltage the capacitor voltage from the source voltage and divide it by the resistor. So that's just basically Ohm's law. And that comes out to be 477.5 microamperes. We could also do that using this formula. And this is going to be the voltage VC initial times e to the negative t over our time constant tau. Now this guy here is missing the 1, which means it's going to be decaying. So what our current would look like if I were to plot it on here, I have not, see that coming up, is it would look like decaying towards 0. And when I work this through, it comes out to be basically the same number as I got by using the simpler approach of Ohm's law. So if you understand kind of what's going on with the circuit here, you can use simple ways of solving problems. Not saying that the exponential is really complicated anyway. Important equation right there. Okay, let's take a look at a discharge. And again, this is the same circuit, and the time constant remains at 120 microseconds, and now I have a switch in the discharge path starting out at 20 volts, and when that switch is closed, current begins to flow from the capacitor through the resistor to ground. So the initial voltage of the capacitor would be 20 volts, and then it would discharge asymptotically approaching 0. So from this we can kind of see what our voltage would be, and at one time constant this should be 63% discharged, and my graphing here is not all that accurate. But to find out what VC would be at 400 microseconds for an example problem, what we would do would take the decaying exponential formula, and let me write that explicitly here. V equals V initial INIT times e to the negative t over time constant tau. So that is the second important formula that we have here. And plugging in our values here, as we see that at 400 microseconds, which would be about here, our voltage is 713 millivolts. So we're getting kind of close to 0 with that. Next we can find VC at 100 microseconds. Same formula, that comes out to be 8.69 volts. 100 microseconds would be about here. So that value makes sense. And then let's do one really weird one, is find VC at 0.5 seconds. So there's a whole lot of time constants in 0.5 seconds. So dividing 0.5 seconds by our time constant, which is 120 microseconds, I end up with 4,167 time constants in a half a second. So capacitor voltage is going to be equal to E raised to this power, and remember this is T over tau, and that comes out to be approximately 0 volts. The calculator shows 0. If we had a lot of precision, it would still give us a very, very, very small voltage sitting out there. So there's some examples on how to use the math to find out the charge and discharge voltage and current of a capacitor. And let's take a little look at this guy. This time I have a source which is negative 30 volts, and I just said 30 volts here because the symbol of the battery is saying that it's negative. And what I have drawn here is the physical current. So when the switch is closed, the physical current is going to charge the capacitor in this polarity, plus and minus. So my time constant in this case is going to be equal to 22K times 10 nanofarad, which comes out to be 220 microseconds. And then to find VC at 100 microseconds, we just use the standard charging equation and multiply it by a negative 30 in this case. So the solution to that would be a negative 10.96 volts. That would be there after 100 microseconds. Now find I at 100 microseconds, and this is where you have to be a little bit careful, because what we would do would be subtract the capacitor voltage from the source voltage. That would be the voltage across the resistor, and then just use Ohm's law. And doing this with polarities is what we see is we end up with a negative current of 866 microamperes. Now, the current is defined, the physical current, in the correct direction. So the actual answer would be 866 microseconds as a positive value. So if I define the current flowing in the other way, it would be in fact a negative value. So you have to kind of be careful when you're looking at the currents with regard to physical currents as defined in the diagram. So if we wanted to find the current at 100 microamps, what we would do would be finding I max. And then we would be using that as a value here, and this is very similar to what we did here. And this would be V. This time is I max, and that requires an extra step. What is I max? Well, if we take a look at it, I max would be equal to, and this would be, or VC is equal to 0 volts, would be 30 volts divided by 22K. So if this voltage is 0, all of the source at T equals 0 plus has to be across the resistor. And Ohm's law tells us that that'll come out to be 1.364 milliamperes. So all we have to do now, and we know that the current is going to decay as the capacitor voltage charges again, is to use our decaying exponential here, and that gives us a value of 865.5 microamperes, which corresponds favorably to the Ohm's law solution that we used before. Okay, let's see here. We have another circuit. We have a 50 volt source, a resistor of 1K, and a capacitor of 22 microfarads. And the question is at what time will the capacitor voltage be equal to 30 volts? And this is quite a different problem. It requires more steps to do that. First order of business, as usual, is to find the time constant. Tau equals RC, and that comes out to be 22 microseconds. Next, what we have to do is solve for T, which unfortunately is in the exponent of our E here, our natural number E. So we have to isolate that. And to do that is we'll divide both sides by V here. And this would be V. Let me kind of put him up here. There we go. And we'll start by isolating the variable is divide both sides by our V here, which gives us VC over V, and that's going to be equal to 1 minus e to the minus t over tau. So that's what we have here. Now we got to clear out the 1, so I'm going to subtract 1 from both sides, and that'll give us VC over V minus 1 is equal t to the minus t over tau. And then working this out with values in it, I have 30 over 50 minus 1 is equal to e to the negative t over tau, or negative 0.4 is equal to negative e raised to the same exponent as before. Now we have a little problem here because we have to do the opposite operation of e to get the exponential value. And the natural operation is ln, the natural log. So if we take the natural log of e raised to something, what that's going to give us is something. The problem is that the natural log is not defined as 0 or any negative values. And here, as you can see, we're sitting at negative 0.4. So what we have to do is convert that into a positive value, and to do that, I'm simply going to multiply both sides of the equation by negative 1. And so doing gives me 0.4 equals a positive e to the minus t over tau. Okay, taking the natural log of 0.4, both sides that is, the natural log of e to the minus t over tau, is we end up with a negative 0.916, and that's going to be equal to negative t over tau. So notice that the natural number here, e, has been eliminated by taking the natural log of it. So in working this out here, what we have, I'm going to multiply both sides by tau to isolate our value t, and that'll give us negative negative 20.158 microseconds equals negative t. Again, multiplying through by negative 1 gives us a time of 20.158 microseconds. Now, that's nice. Is it correct? Well, I don't know. Let's check it. So what we'll do is we'll simply put in our values here, and for t we're going to use our solution, and what we should come out with, hopefully, is 30 volts. In working through this, just like we did before, we end up with a VC equals 30 volts, so I'm fairly confident that the solution is correct. Now, if we were to graph the ln of x, this is what it would look like, and at x equals 1, y is going to be equal to 0. It asymptotically approaches negative infinity as the value of x goes to 0, and it is not defined at 0. The natural log is not defined at 0. So that's what that curve would look like, and that kind of tells why we had to do some shuffling up there with signs to be able to find out what the time would be when the voltage across the capacitor was equal to 30 volts. So that'll conclude. We have followed on here as a little example using multisim, which will kind of show this a little bit, I think, in real time. And if I didn't close in that, let me close now. Thank you for watching. What we're looking at is a circuit that has a time constant of 1 second, which would be 1 ohm times 1 farad. It's being fed by a digital clock source, and we're just using this to replace a 10-volt battery and a switch. So at t equals 0, the voltage here at Vn is going to go from 0 to 10 volts, and the capacitor is going to be charged through this 1 ohm resistor. Now when we run the analysis, my expectation is that the voltage across the capacitor will asymptotically approach 10 volts. So let us run the simulation here, and this is going to be time-based. End time is 5 seconds. And click on simulation, and it's doing the calculations here. Okay, let me make the traces a little easier to see here by increasing the width. this, and now the red trace is the capacitor voltage, and that is starting at 0 when the source goes high to 10 volts. And what we see is that it approaches 10 volts, which would be right here, and it doesn't quite make it. It gets close, but not quite after 5 time constants. Now the industry considers 5 time constants to be a fully charged capacitor. In green, what we see is the current, and the current is going to be highest when the capacitor voltage is the lowest, because at this particular point, if VC is 0, that means that the 10 volts is going to appear across the 1 ohm resistor, giving us 10 amperes. As the capacitor voltage climbs, the net voltage in the circuit, that is the voltage across the resistor, is going to decrease, and hence the current is going to decrease. So at 5 time constants here, the current is very close to 0. Now let's take a look at that 5 time constant point here. Here I'm at 5, and what we see is the capacitor is at 9.9326 volts, not quite 10, and the current in green is 67.3795 milliamperes, not quite 0. So if we look, say, at 1 time constant, is what we would expect to see is that the voltage would be 63% of the way toward the charging voltage, which is 10 volts, and that would give us about 6.3 volts, and we can see that right here, 6.29 volts, so that's pretty close. And likewise with the current at this point, this would be 63% discharged. And then in the second time constant, if we wanted to look at that, and this is a little bit tricky, but the voltage between the first time constant and the final voltage would be 63%. So that would be the voltage between here is 63%, where from here to here is 100%. So every time constant we go out is we converge on 10 volts by 63% of what is left. And the same is true with the current. It's converging on 0 based upon 63% also. So ironically, if we were to take the initial slope at this point, which would be rise over run, and projected it up to 10 volts, that would define the time constant. It would be the initial slope at this point projected here would be 1 time constant. Now, that's a little bit out of our realm, but that's kind of how a time constant comes about. So that's what a charging capacitor would look like, and the charging current would look like, and then the discharge would be quite a bit different.